Alrighty, we got vector applications going on here today. So we're going to look here at this first problem here. You can kind of read through the paragraphs there above. Basically, we're going to use law of sine and cosine to solve these application problems, or this will at least be one of the ways. Towards the end of the lesson, I will go back and to example one and show you an alternate way to solve this one as well here. So you got an airplane is flying with an airspeed of 310 knots and heading at a direction of 50 degrees right there. So let's go ahead and kind of sketch that out here. And I would leave some space to the right, so we're going to write in our alternate method there if you want. So I'll draw, my x and y axis. 50 degrees would look something kind of like this right here. 50 degrees, like a true bearing, is usually three numbers, and that always starts from the positive y-axis. So your 50 degrees will actually go right here. Okay, and then in knots, that's just kind of like your airspeed. That's the unit that they use there. So I'm going to go ahead and put the 310 kind of along that vector line right there, and it's going that direction there. Okay. So next, you do have this wind that is blowing up, and that's blowing from a true heading of 125 degrees. So if we were to sketch that out, I wouldn't draw this, just look here for a second. If we take in consideration that wind would be coming from 125 somewhere over here, but the wind would be blowing this way since they said it's coming from the 125. So what I'm going to actually do is kind of do the big idea of the tip to the tail idea when you're sketching out your vectors. So I'm going to draw like a new x and y axis, and then I'm going to do that 125 degrees right there. And then I'm going to draw the arrow, and I'm going to actually go ahead and extend it here to something kind of along the lines of that right there. So, and I think it wasn't blowing as hard as you're going, so what was this? This one was going at 78 knots. Which, that seems pretty high there, but I guess 78 kind of going that way, a little bit shorter of a vector. And so the big idea, I guess, here is we want to close this up. We want to find, usually it'll ask you for the resultant vector, so that's going to be that green one right there. And that'll be like the true total displacement, I guess. And the big idea is you need some sides of your triangle, which you do have those sides, but you also need some angles to work with. So what we're going to do here is figure out this angle right here. We'll use a little bit of geometry ideas. So to help us out here, I'll work here with the red angle. The 50 degrees will help us get something. What I'm going to do is actually kind of extend that line right there and say, hey, this is a 90-degree angle. And then if I go off to the side and do 90 plus 50, it's 140. We can do 180 minus 140 and figure out that this leftover angle right here is 40 degrees. And that's going to be helpful here in just a second right there. Okay, and then to go find the angle that we're going to need here for this angle, like if I can find that angle, then we're going to be in good shape here. That's going to be congruent to whatever this angle is right here. And since I know that full angle here, we found that that was 125 from the problem, I'm going to subtract off 90, or like this right angle piece right here. And that's going to give me, let's see there, that's 35. And that should be vertical and congruent right there. So that would be 35 as well because of the vertical angles. And now that we have that labeled that way, now we can go and re-sketch the triangle if you want. I kind of like to re-sketch, just kind of reset everything. And then we're going to figure out that green line right there. We'll call that X right there. Find that distance. And we have, the original numbers here. We had the 310 knots. We had the 78 knots going this direction. And then when you combined up those two angles there, the 35 and the 40, you're going to get 75 degrees right there. And then now, from there, we're going to use either law of sines or cosines typically on these word problems to figure out your missing side. With this one here specifically, it would be a law of cosine right there. So I'll stop switching colors. We'll just go with green from here on. So that'll be x squared, 78 squared, 310 squared, minus 2 times 78 times 310. And law of cosine, so you'll put cosine in it of 75 degrees right there. My notes, I can't really read it, so I'm going to go ahead and type it in here. Since you're going to square root both sides eventually, I'm just going to square root the whole thing in the calculator, just let it all do the work for me. And then I don't have to worry about rounding off too much. 78 times 310, and cosine of 75. Double check, make sure. I think that looks good there. 299, and yep, that is, I think, what my notes say here. So x is going to be about 299, and let's just go ahead and round that up to 0.5, 299.5 right there. So that would be the total, I guess, what were we in, speed, I guess, of the plane right there. And that's with the wind kind of helping it out a little bit. Okay, now a lot of times, instead of just the speed or the magnitude part, they will ask for the direction as well. To find the direction, typically, like on the direction, I would probably do the same type of angle format that they did. So they told us like originally it was like 50 degrees or 050, right? So let's figure out this angle here from the red line there to the green line right there. To help us find that, that's going to go with this angle right here inside of our figure. And then I guess what we'll do is take that away from 50. So for that angle there, we'll go and use a law of sines. That'll be sine of, let's just call it angle A, whatever angle you want. Sine of A to 78. And then we have the 75 and the side across from it that we just solved for, the 299.5. So then we'll do law of cosines there on that. When you cross multiply and divide, you'll get 78 sine of 75. And then divided by, I guess, the 299.5. And then to find an angle, you do sine inverse of both sides. That cancels out sine. And then I guess, yeah, we do sine inverse of that whole thing right there. So type that in the calculator. Sine inverse, 78 sine 75. Make sure you close your parentheses. Make sure you type it in right, too. 299.5 comes out to roughly 14.5, really probably 14.6 when you round up degrees. They didn't really tell us what to round to, so I'll go 14.6. You could probably even get away with rounding to the nearest whole degree. All right, now remember here, that's this angle right here, the 14.6 degrees. And since you had that 50 degrees originally, we're going to do, for our final answer here, we'll do 50 minus the 14.6. And then we'll be done. So that'll be roughly 35.4 degrees. So a good way to kind of put this here, you can put 299.5 knots, add a bearing, and then this is where you use the three numbers there. So at 035.4 degrees right there. And that would be a good way to write your answer. So make sure you just put your angle in the same kind of format that the problem started out as, and you'll be good there on that. Okay, so this next part here, we're going to start kind of introducing doing component form of your vectors. We talked a little bit about component form in the last lesson, and we're going to use that idea to help ourselves solve these types of triangle problems. We're going to do that same problem that we just did with components in just a moment. We'll probably do it here at the end. So let's roll through this one here. You got two or more vectors with a sum that is the vector R are called components. You have different components that add to a combined vector, I guess. While the components can have any direction, it's often useful to express or resolve a vector on the two perpendicular components. The components of a vector are going to be horizontal and vertical, or that's like kind of the ones that we're going to use, a horizontal and vertical component. So we'll start out with this one here. They're only going to give us one vector. You got Jamie is pushing the handle of a lawnmower with a force of 450 newtons at an angle of 56 degrees with the ground. So let me sketch that out there. 56 degrees right there with the ground. And she's pushing he or she, I guess, is pushing right there. So you can put your 450. So, imagine like this is like the lawnmower right there, and you're kind of pushing it up against it right there. We'll worry. So since it's going left and down, we'll worry about the signs part here in a minute. But just to review over finding the components. Yesterday we talked about you take your magnitude 450, and then you do cosine of your angle 56 degrees, and then that'll get you your x component right there. So apparently, according to my notes, I got 251.63 when you do that. For the y component, it's usually tied to sine. Oops. And I got here 373.07 right there. Okay, and you can go and get these numbers, like you can go get this whole thing, like the component form. You can set it up like a right triangle trigonometry problem here with SOHCAHTOA, but when you solve it, it will be in the calculator 450 times cosine, and then 450 times the sine of 56. So that's kind of like the picture in the sketch there. They want the magnitudes there, and then find the magnitudes of the horizontal and vertical components. So like find this piece going backwards here, and then this piece going down. And really the only thing I'm going to do here is just make sure it's negative. Like I'll take those same numbers we got, but instead of saying going right, 251 right there, I guess I'll say it's going backwards, 251.63. I guess it's kind of tied to the way you draw it. Right or left, I guess the x could change. But there is definitely a downward force going on, so your y should definitely be negative here, regardless of the way you sketch it right there. And that's just because the force is going down. So there you go. That's how you do components right there. So this next section here, we're going to be using components to help ourselves solve this vector problem. And you can still solve example 3 the way we did example 1 up here, but they want us to try and use some different components here for this. So the way I'll do this typically with multiple vectors is when you're doing component form, you can use like the same picture, I guess, but you're going to have like different components for each vector. So I guess let's just draw maybe one picture. You got a quarterback, he's running forward at 5 meters per second. So you kind of, in a way, have a vector, and it's going to look like this. He's going 5 meters per second, and it's horizontal, so you could even say it's, at 0 degrees there, which can help you a little bit with your component form. He's also going to be throwing a football, and it's at a different angle here. It's going to be at 40 degrees, kind of like that. And he's throwing that at 25 meters per second. So typically you'll make the vector a little bit longer. That's being thrown at that speed there, 25. So now usually they'll say, what is the resultant speed and direction of the pass right there? So basically what is, with him going forward and then throwing at 25 meters per second, what is the true speed of the ball there? So here's how we're going to do this here. I'm going to actually color code this here. I'll do the components for this one here in red. And it's quite simple. You can honestly use a little bit of logic here. Your x component should be just 5 meters per second. And it's going to come out to 5. If you do 5 and then cosine of 0 degrees, cosine of 0 typically is 1. 1 times 5 is going to be 5. So you're going to go 5 to the right with that. And then if you do the same thing with y, 5 sine of 0 degrees, that actually comes out as 0, which means that vector is going 5 to the right and not going up at all, which kind of makes sense there. So this is your component there. If you want to write it in component form, you could write 5 and then 0 like that right there. Okay, next what we're going to do here is do the component form here for the second vector here. I guess I'll do this one in purple. So that was the 25. So we do 25 cosine of 40 degrees right there. You got a different angle too, don't forget about that. And then y, that vector is going at 25 for your magnitude sine, and then that was still the 40 degrees right there. And we'll just type those in there. Cosine 40, so that's roughly 19.15. And then we'll change it to 25, and then sine of 40 degrees, that was 16 point. Let's do 0.7 right there. So if you do your component form, 19.15, 16.07. So the big idea yesterday, we talked about adding multiple vectors in component form. So all you're going to do here is you're going to add these, and this is going to get your true component form, I guess. So if you add those there, the 5 plus the 19.15, I guess I could have done that in my head there, 24.15, and then the 0 plus the 16.07 would just be 16.07. So like the true overall vector, if you want to sketch it out here, is going to look like this here. It's going to go 24 to the right and then about up 16. Just like that right there. So if you want to actually find the true vector there for that, which is what they're asking, what is the resultant vector right there? Now you can go and kind of use your magnitude formula or Pythagorean theorem, however you think about it there. So your magnitude of it, do they have a name for this vector? I guess they don't. I guess I'll call it V. The magnitude of V, just in the calculator, 24.15 squared. And the 1607 squared. Make sure if you got negatives with those for whatever reason, you go ahead and throw some extra parentheses around it. Kind of like this here. It's not going to make a difference since these are both positive, but you would want to type it in just like this here to the right. Squared and then plus parentheses 16.07 squared. And apparently that comes out to 29, and I think that's what I got here in my notes too. So your magnitude of your vector is about 29.01, I guess, after rounding. So that's your true resultant speed. It's a little bit faster than the 25, and that's because you got that forward movement. And then a lot of times they'll also ask you guys for the direction of it. So let me kind of make that a little bit smaller. As far as getting the direction of it, it's essentially just asking for your angle. And we'll just set up a tangent equation for that. We'll say tangent of theta equals the opposite over the adjacent. It's going to be, your y over your x. And then to type that in the calculator, that you do tangent inverse. 16.07 divided by 24.15. So theta is roughly 33.6 degrees with the horizontal. So that would be your answer there, and then the 29.01, I guess, meters per second would be the other part of your answer right there. So that is using component form. Now, you can do the whole idea of doing your parallelogram, sketch that out, making it into a triangle, and then using the idea if this angle's here is 40, then this angle up here is 140 and 140, and then use law of sine and cosine. You can still do that there, totally fine. It's actually, in my opinion, just a hair quicker. Where the component form really starts to shine is when you have three vectors, and that's coming up here on this one. So this one's got three vectors, and it is too big of a pain in the butt to do your tip to tail little method thing with three vectors. Basically, you do two at a time, and then you get your result. You take that result, you do it with the last one, and then you get your second result, and it basically turns it into two problems. So something like this with three forces, I would, if I were you, do component form, just like we did. Just this time we're going to have three. All right, so I'm going to color code them here since there are three. Kind of gets a little bit messy here. So the first one was at 30 degrees. Put that. That was at 70 pounds of force. And then that was at 30 degrees. The second one was 40 pounds of force. So I'm not going to make it as long, but it was at 45 degrees. Not quite as long, so something like that right there. Draw my arrows. So I'm going to draw that angle, and that was 45 degrees. And that was at 40 pounds. And then finally you had the 60 pounds one, so it's kind of like a medium length. So we'll do that here in purple, and that was going at 120 degrees with the horizontal. And that was, what was that, 60. Okay. So we're going to do component form for each one of these here. And I would recommend you color code them, honestly. And from yesterday, we talked about just, for your components there, you do 70, and then for x is cosine, so cosine of 30 degrees. And I already got that written down. That is 60.6. For the y part here, that would be 70 sine, and then 30 degrees. Apparently that comes out to, well, that comes out nice and clean there. 35 is because it's one of the nice ones on the unit circle. All right, for the blue vector here at the 40, so the x part would be the 40, and then cosine of 45, and that'd come out to 28.3. I've already punched those out. You can feel free to type those in the calculator yourself if you would like. Actually, sine and cosine of 45 degrees on the unit circle come out to the same thing, so it's not a coincidence that these come out to the same thing. And then finally, we'll do the purple one here. That was at 120. So, whoops, so 120 degrees. What was the force? The force is 60. 60 cosine 120. That came out, and it actually comes out to negative 30. That makes sense because the vector is going backwards here. Okay, so going backwards, negative 30. The y should still be going up, so the y should be positive here. So that's 60 sine 120 degrees. It should come out to 52.0 according to my notes. So once you get all of your x's, you're basically going to add all x components, and then after that, add all the y components. And that'll get you, I guess, your resultant, horizontal and vertical components there. So for the x part here, we're just literally going to go 60.6, and then plus 28.3, and then plus the negative 30. Or really, you could write it as minus 30. You should get 58.9. And then when you go and add up the y's, I already got them added up here. When you add up all your y's, the 35, the 28.3, and the 52.0, you're going to apparently get 115.3. So that's kind of like what you get right there. Then I like to resketch it. You don't necessarily need to do this, but I'm going to resketch the resultant vector. So this is like the sum of everything here. I don't really know what the angles are, but I know it's to the right 58, roughly 60, and then up 115. So it probably looks something kind of like this right here. Okay, and then I'll put in my 58.9, 115, and then 0.3. And then you're going to find the length of that hypotenuse of that triangle. So use your magnitude formula, which will be 58.9 squared, and then 115.3 squared, and then square root that. And unfortunately, I can't see that in my notes. I'm going to have to type it out. My notes are black and white, and they're highlighted, and there's not enough contrast in the color, so 15.3 squared. All right. So apparently we get 129. That makes sense too, because it should be the longest side of your triangle there. So 129.5, I guess we'll say newtons. And then once again, to find your angle, you'll set up a tangent equation. Some of y'all might even skip this and skip straight to typing it into the calculator. But tangent inverse of 115.3 over 58.9. Second tangent. All right. So then that's going to be at 60, let's just round that up to the nearest whole number, 63 degrees right there. That's how you're going to do those there with three components. So the three components, a little bit tricky there on those just because there's a lot there for each of those, but that is how you do that. So I do have one I like to add in here, finding the resultant vector between two vectors, and they just give you 32 degrees. So I'll do that, but before I cover that, I want to show you back here on that first problem. Copy this. So I reworked that same first problem. I'm not going to do every little step here, but I wanted to kind of squeeze this in and show you how it kind of ties in. So, the first problem, we had the little triangle drawn up here. We got our sides, we made our triangle, and we did a lot of cosine and sine here. But you can split it up and do your component form of your vectors, which is what I did here. Now when you do it though, you do need to make your angle with the horizontal. So instead of using the 50 degrees that we originally started with, I did 90 minus 50 to get 40 with the horizontal, and then that way we can do our horizontal and vertical components there on that. So you just get that side and that side going up and down there. Those were those components. Did the same thing with the other triangle. You do have to do some manipulation here because your component with the horizontal is going to be this right here. And I go, and I kind of can walk you through the math there over there to the right, but eventually you get 145 degrees right there for your true angle, and then you'll do 78 cosine 145, 78 sine 145. You add them up, and then you'll get your horizontal and vertical components, and then you should get the same thing. We got 299.4 on the first one, which I believe matched hopefully fairly well with what we had. 299.5, just a little bit off on the rounding, but essentially the same thing there. So that's another way you can do those there. You can really work in both ways there. The only thing is with 3 vectors, I would definitely do component form. I would stay away from trying to do the triangles there on that. So let's end here with this one here. It's a good one to end with. 2 forces, magnitude of 50 and 45 newtons act on an object with an angle of 32 degrees between them. Find the resultant vector. So there's a couple ways you can draw this, and I actually wouldn't draw it this way that I'm about to show you here. So you could put your vectors like that right there and then put 32 degrees. And then it's sometimes a little bit hard to get the triangle sketched out, or the parallelogram, because your resultant vector is going to be somewhere here in the middle, something kind of like that right there. So in my opinion, I think the best way to draw this here, hint that I would do, is draw one of your vectors along the x-axis. It actually makes it much, much easier. So just pick one of them, the 50 or the 45. I guess I'm going to pick 50. Going along the x-axis. And then put the 45 newtons between. Oh, and it's at an angle of 32. Let me make it a little bit smaller. So this one's not quite as long. That's 45 newtons, and then the angle between them is 32 degrees. So if you conveniently make it to where one of the vectors is going along the x-axis, it's a little bit easier to draw your little triangle and parallelogram that you're going to need here. You can also use the whole idea with component form if you want to do that, but I'm going to rework this one. I'm going to do it with the whole idea with the triangle and everything. So I'm going to copy over that 45 newtons. Get your tip to the tail right there. Go ahead and copy up the 50 newtons up here at the top. And then your resultant is going to be where those meet up right there. So I didn't do it perfect there, but whatever. Okay. Be careful. A lot of people sometimes divide the angle, like divide that 32 right there. But since, one of them is a little bit bigger than the other, it's not always divided by 2. It's actually hardly ever divided by 2. To find the angle you need, use the idea that these 2 angles here on a parallelogram add up to 180 degrees. So if you do 180 minus your 32, you're going to get 148 degrees there, and then 148 degrees there. Okay. Now, you have 2 triangles to work with. I usually work with this bottom one, because one of the angles is formed with the x-axis. It makes the angle part a little bit easier at the end, so I'm going to do that triangle right there. And then it's actually pretty similar to one of the ones we looked at earlier, where you use law of cosines. On this here, you got 50, you got 45, and then you found your 148. So now we can find that distance right there for your result vector. So as far as law of cosine, this would look like this right here, 50 squared. 45 squared minus 2 times 50 times 45 cosine of 148. Let me see here. I think I got this. Oh no, I don't have this written down. Okay. And then you would square root that whole thing. So I'm going to go ahead and do that. Okay. Theoretically, if I type that in correctly, you get x is about 91.3. That does make sense because that should be the longest sides across from the biggest angle. 91.3 sounds about right. To find your angle, we'll call this angle here A or theta or whatever you want. We'll use the law of sine for that. Law of sine says sine of A over 45 and then equals sine of 148 and then over the 91.3. And actually, I'm going to use this one here to show you a little tip here. So if you don't want to have to do any rounding or anything, you could take that previous answer that we got, that 91.3. You can actually just hit second and then negative, and that'll type in your previous answer. So watch this here. I'm going to go sine inverse. That's going to be 45 and then times sine of 148 and then close parentheses. And then instead of dividing by 91.3, I'll divide by, and then I'll do second answer like that right there. And that'll type in the previous answer. That'll give you the most accurate answer you could possibly get. Usually it's not going to be that big of a deal that if you don't do that, but this is how you get a fairly accurate answer. Let's round that up to 14 right there. Okay, so there's your angle right there. Now, as far as like how do you write your answer, you don't want to say the angle's made with the horizontal because it's kind of made with this vector right there. So the way I'm going to write my answers, I'm going to write it as 91.3. I think it was in newtons, right? Newtons at 15.14 degrees from, and then don't say the horizontal, say from the 50 Newton vector. Most teachers are going to be cool with you just putting in just the angle there, but I like to put it's from that 50 degree Newton vector right there, so it's about 15 there. If you want to find the other angle up here at the top, I guess you don't need to do this, but you could do 32 minus that 15 degrees there, and that gets you 17 point something or 16 point something right there. So anyways, that'll be it here for today.